Chapter 2, on Osmolality and Tonicity. Revising the definitions, 1 molarity is number of moles of solute in 1 liter of solvent. 2. Molality, number of moles of solute in 1 kilogram of solvent. 3. Tonicity, number of effective osmoles that can exert the osmotic gradient across the membrane. For example, sodium and chloride. What is serum osmolality? It is the measure of the concentration of solutes in the blood. It reflects the total number of dissolved particles per kilogram of plasma water. The dissolved particles can be anything like sodium, glucose, and urea. It is an important parameter for assessing the fluid and electrolyte balance in the body. Normal range of serum osmolality is 275 to 295 milliosmoles per kilogram. Formula is 2 multiplied by sodium plus blood urea nitrogen, which is divided by 2.8 plus glucose divided by 18. For example, if the serum sodium is 140, blood glucose is 90 milligrams per deciliter, and blood urea nitrogen is 50, then what is the serum osmolality? By putting all the above-mentioned numbers in the formula, the serum osmolality of this particular example is 290.36 milliosmoles per kilogram. What is the difference between millimole and osmole? Millimole refers to the quantity of a substance irrespective of dissociation, or it measures the amount of a substance, whereas osmole refers to the osmotic effect that a substance will produce in solution, or it is the measure that is the contribution of the solute based on the dissociation in solution. Let us know a few examples. How many osmoles are there in 0.9% of sodium chloride solution? Answer. Step 1 is 0.9% of sodium chloride is 0.9 gram in 100 milliliters or 9 grams in item milliliter. Step 2 is finding out the molecular weight of sodium chloride, which we already learned in Chapter 1. If you haven't checked out, please refer the link provided. So, coming back to Step 2, the molecular weight of sodium chloride is 58.45 gram per mole. The number of moles of sodium chloride in 1 liter is the mass of sodium chloride divided by the mole of weight of sodium chloride, which is 9 grams divided by 58.45 gram per mole, which is 0.154 mole. 1 mole is 1,000 millimole, then 0.154 mole is 154 millimole, giving 308 milliosmoles per liter. Thus, 0.9% sodium chloride contains 308 milliosmoles per liter. It is iso-osmolar solution because the solute particles in the solution are nearly equal to that of the plasma, and it is isotonic as the osmotic pressure is also same as that of plasma. Next example is 0.45% sodium chloride solution. 0.45% sodium chloride has 0.45 grams in 100 milliliters, or 4.5 grams in 1,000 milliliters. Putting that into the formula, we get 0.0769 mole, which is equal to 76.9 millimole, which is 154 milliosmoles per liter. Thus, 0.45% sodium chloride contains 154 milliosmoles per liter. It is hypoosmolar because the solute particles in the solution are lower than that of the plasma, and it is hypotonic because the solution's osmotic pressure is less than that of plasma. The next example is 3% sodium chloride solution. The 3% sodium chloride solution gives 3 grams in 100 milliliters, which is 30 grams in 1,000 milliliters. Putting all in the formula, we get 0.5137 mole, which is 513 millimole, and 1,026 milliosmoles per liter. Thus, 3% sodium chloride contains 1,026 milliosmoles per liter. It is hyperosmolar as the solute particles in the solution are higher than that of plasma, and it is hypertonic because the solution's osmotic pressure is higher than that of plasma. Next example is 25% dextrose, which is 25 grams in 100 milliliters or 250 grams in 1,000 milliliters. Molecular weight of dextrose is 180 grams per mole. So, applying into the formula, we get 250 grams divided by 180 grams per mole, which is 1.3888 mole, which then is 1,390 millimole, and it is 1,390 milliosmoles per liter. Thus, 25% dextrose contains 1,390 milliosmoles per liter. It is hyperosmolar because the solute particles in the solution are higher than that of plasma, and it is hypotonic because dextrose gets metabolized in the plasma. Next example is 8.4% of sodium bicarbonate. 8.4% sodium bicarbonate is 8.4 grams in 100 milliliters or 84 grams in 1,000 milliliters. Molecular weight of sodium bicarbonate is 84 grams per mole. Applying all these values into the formula, we get 1 mole. 1 mole is 1,000 millimole, and the osmolality is 2,000 millismoles per liter. Thus, 8.4% sodium bicarbonate contains 2,000 millismoles per liter. As the solute particle in the solution is higher than that of plasma, it is a hyperosmolar solution, and it is hypertonic because the solution's osmotic pressure is higher than that of the plasma.